So yeah, my name is Robert. I'm a committer and PMC member of the Apache Flink project. I'm employed at Data Artisans, a company which we founded 1 year ago in Berlin, in Germany. It has been founded out of the main developers of Apache Flink, the main committers. Before I start with a more in-depth technical stuff, I will give a bit of a history overview over Flink. So in April 2014, we added Flink to the Apache incubator. So the incubator is the project where new or existing projects enter the Apache Software Foundation. Back then the project was still called Stratosphere. That's the name of the research project that Flink originates from. And 3 releases after we entered the incubator and after we renamed the project to Flink, Apache decided to make it a top-level project of Apache, which means that they acknowledge that the Flink community is grown up and that it's able to govern itself. And since then we are an official top-level project that is able to do releases on its own and so on. And if you look to the last stable release, 0.9, this summer, you can see that the software stack of Flink has actually grown a lot. So when we entered the incubator, Flink was just the core, some deployment options, and the batch dataset API on top of it. And a few months afterwards, you can see that we have added a streaming API on top of it, and we have added a lot of higher level abstractions for specific use cases like machine learning or graph processing. And we also added more deployment options and so on. And as we speak, we are about to release 0.10. So currently we have release candidates and votes going on, and I hope that the latest vote goes through. So that usually we find some bugs and we cancel the vote and we start a new vote and so on. But I'm confident that the current release candidate is also going to be the final release of Flink 0.10, so we can probably expect it this or next week. And the next big step is then Flink 1.0, which means that we guarantee API stability across all minor releases of the 1.x series of Flink. And this is pretty impressive, and it's we didn't do this on our own. We rely on a huge community which is always growing. It's a very vibrant, diverse community from all over the world. And we are also one of the largest and fastest growing big data projects within the Apache Software Foundation. You can also see that we are not like a German or European project. We are a worldwide project from the Meetups, which are popping up all over the world. So I recently created the Munich Meetup group. So if you want to learn more about Flink, hopefully we'll have more talks in the future here, maybe next year. But we also have meetup groups, for example, in Chicago, New York, and San Francisco, also in Asia. So all over the world, people are creating meetup groups to share their experience with the software. There are also a lot of companies, research institutes, and universities behind Flink. So this is just the list of organizations or the logos of the organizations which were at Flink Forward, so which were speaking at Flink Forward. So Flink Forward was the first conference on Apache Flink, which was held in Berlin a few weeks ago. As you can see, it's quite a few prominent names which are using Flink, contributing Flink, and so on. Also a lot of news outlets, websites, blogs, and so on are reporting about Flink. So you can see it's a very diverse community out of different backgrounds which are talking about Flink, using it, and so on. And all this excitement is about this new hot stuff in the big data space, which is stream data processing. Maybe fast data is becoming the next big data. Let's see, I think right now there's no new fancy word for this. But the question is, why are so many people talking about stream processing right now? And in our opinion, streaming is the biggest change in the data infrastructure that we had since Hadoop, because we changed the way how we think about data. And it's also that currently the infrastructures are working around the limitations of the available systems, by building up complex, I don't know, Lambda architectures where they have a batch layer and a streaming layer, and where they, I don't know, start batch jobs every 4 hours to somehow work around the issue that there's no good stream processor. And with the availability of enhanced systems like Kafka and Flink and so on, you can actually make your infrastructure much easier, because you don't need all these different systems to achieve your goals. In addition, new use cases like IoT or on-demand services demand for new systems. Like Uber, for example, they have this, they can identify when a certain area is very popular, then they can increase the price of that area. And that feature needs to have a streaming system in the background to identify which area of the world is currently popular. So they need to identify, okay, Oktoberfest is happening, and we have to increase the prices. With a batch system, you cannot do this. And third, you can subsume all the batch use cases with a good stream processor. So you don't need a batch processor, you can just use your streaming system to also run your batch use cases. At Flink Forward there was a great talk by Google, and this is also the direction where Google is going. They are also replacing the existing infrastructures with a stream processor, also for batch use cases. So for the batch space, there are very good systems out there. For the event or real-time processing space, we need new systems. And these new systems, they reflect the fact that real-world data is unbounded and pushed to the systems. What this means is, for example, if you imagine a web server where you record every click of the user, what people are doing right now, they're writing a log file. And then they put this log file into HFS, and then they run their Hive or whatever on these log files to understand what their users are doing. The issue is, you understand what your users are doing hours later, like, I don't know how long this pipeline needs, but you get the results with a certain delay. And these streaming systems, for example Kafka, where you ingest all these events to, and Flink, which take the data out of Kafka again and analyze what the users are doing, these systems are able to give you the result or give you the information what users are doing with a much lower latency. So for explaining how systems are able to provide for all these things that I've promised here, I'm going to explain you why Flink is a stream processor with many phases. So with many phases, I mean we can be a good system for very different use cases. And the very core of all these, to support all these use cases, we have our core engine. And this engine is able to process batch workloads, but also streaming workloads, machine learning, graph processing, and so on. So for the next few minutes, I'm going to explain you how the engine, the runtime of Flink, how it works. And for building such an engine, we looked at the requirements that people have when they need such a system. And the first requirement is low latency. So people want to have fast results within milliseconds. For example, if you have an alerting system which detects credit card fraud, you want to lock the credit card as soon as you see that there's fraudulent behavior. The second requirement is that you want high throughput. So in case of, I don't know, your website gets popular overnight, or it's Christmas and you run a shopping site, you want to handle large data amounts. So you want to be able to handle millions of events per second. The next requirement is correctness. So people want to have exactly once guarantees in streaming systems. Current systems like Storm only have exactly once have only at least once guarantees. With Flink you can actually get also exactly once guarantees. So this means that when some components of Flink fail while processing, we can restart them and we can reinitiate the state of your operators and so on, so that you don't see from the outside that something has happened in between. And the last feature here is programmability, intuitive APIs. I think many people coming from the batch space are used to easy to use APIs. In particular, for example, if you're a Java programmer, you're used to collections and then you do some transformations on the collection and so on. And people want to have similar APIs also for stream processors. And that is what Flink is giving you. So for achieving these requirements, one building block is pipelining, pipeline execution in the engine, which means that all the operators, whether it's a batch program or a streaming program, are online all the time. So we try to keep data moving all the time. We try to materialize data as, we try to avoid materializing data at all costs. And this comes in handy also for streaming programs, where you have, for example, a data source, for example Kafka, and then you have an operator which is splitting the elements from the stream, for example strings, into smaller strings, and then you have a window operator. And the interesting observation here is that these operators push data immediately forward as they receive it. So there's no waiting or buffering involved, which means that we have very low latency because the elements go through the system immediately. And also this repartitioning step, where you regroup your data over the network, is pipelined. So there's no traditional batch processors have a waiting step here, and once this stage has finished, the next stage is deployed and consumes the data from the previous stage. And in Flink we have a this pipeline engine which can also do repartitioning in a pipeline fashion. We also have some more fancy features in this part of the system where we handle, for example, back pressure very nicely by having basically bounded blocking queues between these operators. So we can easily back pressure when, for example, the window operator is slower than the data source. They start slowing down, and then they will just slow down consuming data from Kafka, which is a very nice feature that other systems are suffering from. Next is fault tolerance. So there are two main fault tolerance guarantees that systems have. One is at least once, which means that you make sure that all operators see all events, but it can happen that you see events multiple times. This is okay in cases where you, update a key value store, for example. Then you just update one key twice, but you don't have any false results. But I don't know if you want to do accounting, or I don't know if it's about money or so, then you want to have exact results. You want to make sure that your counting always adds up, also in case of a failure. And that's where exactly once comes into play. So there we ensure that operators do not perform updates to the state multiple times. So in case of a failure, we are able to restore the old state before the failure and then continue with the processing. And there are two approaches for this. So Flink is using distributed snapshots. It's an algorithm that has been, a variant of the algorithm that has been proposed by Jandy Lamport quite some time ago. And Spark is doing micro-batches on their batch runtime. So the Spark approach usually leads to very high latencies because these batches are basically the limitation for the latency. So if you have a batch size of 5 seconds, your latency is always at least 5 seconds. In Flink you have a much lower latency. And these distributed snapshots, you can imagine them, so you have a data source, the Kafka consumer, and you have a counter. So a very simple topology where you just read something and count how many elements are in the Kafka topic. And these two operators have operator state. In case of the Kafka consumer, it's the offset within the partition. So for a very simple case, you have just a topic with one partition, and the offset is basically just the position inside the stream in Kafka. And the counter is just counting how many elements it has seen. And a very simplistic approach for doing a snapshot of this is by stopping everything, taking a picture of the state, so just remembering these two numbers, and then continue with the processing. So that's a very simplistic approach for doing a snapshot of the state. The problem here is, of course, if you stop the whole topology, you reduce the throughput and you add latency, because every time you stop it, you have to wait. And what Flink is able to do, it's able to do a snapshot, a complete snapshot of the state without stopping the topology. So we are basically taking small pictures as we move along the operators, and then we put the picture together again. And this way we can, we have valid states that we can restore from in case of a failure. So if this element counter fails, or the machine that runs this element counter fails, we can just use the last valid state and put the state here and put the state here and then start consuming again. So this counter will always be correct. The counter will always be in sync with the Kafka, with the elements in Kafka. And we do this by pushing barriers through the stream. So we send the normal data, and sometimes we send a barrier. And every time an operator comes to the barrier, it takes a snapshot. And once the barrier reaches the end, the checkpoint coordinator knows, okay, now the picture is complete, this checkpoint is valid. So everything before the barrier is part of the snapshot, everything behind the barrier is part of the next snapshot, basically. So it's a very lightweight approach of doing state backup in a streaming system. And you can also configure how often we insert these barriers into the system. So you can configure the trade-off between latency and throughput and the time you need to restore. So if you have a barrier frequency of 10 seconds, then it might happen that you lose your processing worth of 10 seconds. But I think everything up to 500 milliseconds, so 500 milliseconds is certainly possible for these barriers. It depends on the size of your state, of course. And you can store the state in memory, and you can also store it in file systems. Speaking about APIs, this is the streaming API of Flink. And on the first slide, it might look like, I don't know, the Scala API of Spark, of the batch API of Spark. But it is a streaming API. So instead of a data set, we have a data stream here. And these are the transformations that we apply to the stream. So we have a flat map operation and we have a map operation. So in the flat map, we split the stream. In the map operation, we turn the words into these word count case class elements. So case class is just a Java class with two fields, word and count. And you can also see our API is very nice when it comes to grouping and joining and so on. You don't need to, in other systems they have these key value pairs, in Hadoop for example, I think also in Spark, in the RDD API. And here you can just randomly select fields from your object for the grouping or joining key, which makes it very easy to join on different fields. Then we have this window operation, so here you should realize that you're in a streaming program and not in a batch program, and some operation for doing the word count. And the interesting observation is that this is just a regular batch word count example implemented as a streaming program. So what we do here is we create one global window, so one window that has the size of the entire data stream. And the data stream is just the entire file that you want to count the words on. And then inside this window, we count the frequency of the terms. So this is how you can run a traditional batch workload on a streaming system. By just creating one big window, putting everything into the window, and then do your computation inside the window. But for this only works because this file is finite. So the file ends at a certain point of time. So when the file has been completely consumed, it's over. But if you have a stream that never stops, I don't know, like a stream from your website where people are clicking on your shopping website, then you need to do windows which are for example time-based. So then you can define a window of 1 hour or 1 day or whatever, or a tumbling window which is always tumbling over to process a stream which never ends. And then you can do your computation inside this window. Of course, we also have a batch API. So this is the data set API. So instead of a stream, you have the set. And there you can also express word count very easily. In the batch case, we also have a sophisticated optimizer, which is similar to cost-based optimizers in regular database systems. So we automatically decide the most efficient execution strategy for your program, depending on the data size and also depending on the cluster. So that's also a unique feature of Flink for batch processing. So to summarize the requirements, we have low latency thanks to the pipeline engine. We have exactly once guarantees with the distributed snapshots. It's a very nice approach compared to mini batches. We have high throughput by controlling the checkpoint overhead. And we have APIs which are very similar to those known from the batch world. Somebody asked before the talk for some performance numbers, and we measured Flink mainly against Storm to see where we are standing. And this is a very simple benchmark which doesn't involve any network transfers, so we just generate data. In this case, we just generate some text, some strings, and then we have a second operator, we have grep operator, which is grabbing or searching for certain regular expressions within this stream of strings. And these two green bars, where you can see that Flink, these two green bars are for Flink, and that's the aggregate throughput of a 30 machines cluster on Google Compute. And the throughput is 175 million elements per second. Running the same job in Storm, we only achieved 9 million elements per second on the entire cluster. The thing is, Storm hasn't been optimized for high throughput. Storm is optimized, I think Storm has been mainly developed by Twitter, and they care about latency. So Storm is mainly about low latency and not high throughput. And you can also see the difference between these two bars is that here we have exactly once enabled, so we do checkpoints every 5 seconds. Here we don't have any fault tolerance. And you see that the bars, the performance is almost the same. So the impact is not much when enabling guarantees or not. But the state is also extremely small in this case, so it's not really relevant. This is a more involved benchmark because now we also have network transfer. So now we need to, what we now do is we group the elements, regroup the elements after the data generation. So in the yellow circuits we generate some benchmarking data, basically, very small records. And then we send them over the network to the consuming machines, which measure the latency and the throughput. Since we are regrouping the data over the network, there need to be network connections between all the machines, which leads to network transfer. And here Flink was able to achieve an aggregate throughput of 83 million elements per second over the entire 30 machines cluster. Storm without any fault tolerance, 8.6 million. And Storm with at least once activated, only 309,000 elements per second. This is due to their how they do the how they implemented that at least once. So they basically do a confirmation on a single tuple basis. So it's extremely expensive what they need to do per individual record to all acknowledge them when they have finished processing. And in Flink we have this very low overhead checkpointing mechanism where we just send barriers through the system, which is much cheaper. Then we also measured the latency in the same job. And here you can see that the latency for Storm, the median latency for Storm, is actually better than the latency of Flink. But this is only the median latency, which is like the 50% guarantee of, so 50% of all the elements are at 25 milliseconds or below. And the 99th percentile is for all the systems at 50 milliseconds. So we can guarantee that for 99% of the data, they have a latency lower than 50 milliseconds. The cool thing about Flink is you can influence, you can trade off the latency with the throughput. So we have something called the buffer timeout, which allows you to change the behavior of Flink with respect to latency. This buffer timeout, so I've showed you this slide with a pipeline execution, and we don't send the records individually over the network, so we don't do something like these complex event processing systems do. We have network buffers where we put the elements in, and then at some point we send these network buffers to the other machine. And the problem is if we wait for too long with sending these buffers, the latency goes up. That's why all these buffers have a timeout. So after a certain timeout, we just send this buffer whether it's full or not. In a batch system, you send the buffer when it's full. Then you have then you can send the most elements per network transfer. in the streaming case, you can set a timeout for these buffers. The default timeout is 100 milliseconds. And here in this experiment, you see that we try different values for the buffer timeout. So 0 means we send the buffer immediately for every record. Then 5, 10, and so on until 100 milliseconds buffer timeout. And you can see in the green bar the latency. So for a buffer timeout of 5 milliseconds, the latency is below 10 milliseconds. But the throughput, the yellow line, is also kind of low. So there you have only 20 million, less than 20 million elements per core, per aggregated cluster. But as you increase the buffer timeout, the latency goes up and the throughput goes up. So depending on your use case, you can fine-tune the system. The last thing that we also verified with experiments is the correctness. So our exactly once guarantees and also this whole buffer pushing mechanism. And what we did here is we implemented 2 Flink jobs. One job which was generating data into Kafka, and a second Flink job which was reading the data from Kafka again, validating that everything is correct. So we just used a state machine on the generator to produce valid state transitions, and a state machine in the consuming job to verify that we are only doing valid state transitions. And this can only work if you process the elements in the same order as they were inserted, and if you always back up the state of the state machine. And the red line is the throughput of the data generator, and the blue line is the throughput of the data consumer. And every time you see this vertical green bar, we killed one of the machines of the consuming job. So every time the job lost a machine, it needed to restart the topology and to put in the valid state of the state machine into all the machines. This is also why you see that the throughput for the consuming job goes up every time one machine has failed. And the reason is that this producer is always producing. But when one machine was failing, we needed to stop the topology quickly and redeploy it. And during that time, we were not able to consume data, and that's why it needs to pick up basically what we buffered in Kafka. This is also why we really recommend users to use Kafka in front of Flink to have a layer which is able to buffer data in case something fails and so on. So yeah, you can see we had like 10 failures over like I think 1 hour or so, and the state machine was always producing correct, valid state transitions. In the beginning we had some bugs in our state machine, and every time we had an illegal state transition I was drawing a vertical red bar. So there are no red bars, so it's working. The code is open source, you can try it yourself. So to summarize the performance section, continuous streams with latency-bound buffering and distributed snapshots leads to high throughput and low latency, and you can actually influence the latency and throughput depending on your use case and your requirements. In the beginning I was talking about the different phases of Flink, and I would like now to go a bit through these phases and tell you what Flink has to offer for different use cases. So one big use case, and I think it's also the main use case of Flink, where we look at what users are doing in production, it's stream processing. The next big use case, and that's also where we are coming from, is batch processing. Interestingly, when we created this engine, we didn't have these streaming use cases in mind, but we were designing it already as a pipeline engine. And other SQL systems like Impala from Cloudera, for example, is also a pipeline engine. So they have similar features in the engine as Flink. So it's, I think, from the research point of view, it's the best way of implementing a good batch or SQL processor. And then we also support machine learning use cases and graph analysis use cases. So Flink has support for iterations built into the system, which means that the system is aware that you are executing iterative algorithms. Spark was improving on iterations compared to Hadoop because they have this in-memory caching. In Flink we can further improve on this because our optimizer is actually able to optimize also iterative algorithms, and our engine can do more optimizations because it's aware that it's executing a cyclic data flow. explaining the phases of Flink, we are now going to complete the stack of Flink. So I've already explained to you the engine, the core, and next is all these boxes that I'm going to complete with you. The first boxes that I'm going to complete is the APIs. I've talked about this already, sorry, my slides are a bit hacked together, so I'm skipping this. So there are two main APIs, which are not very low level, so they are for users. They are not intended as, I don't know, intermediate APIs. We try to make them as nicely as possible, and they are similar to, so everybody who's a Java programmer should feel home in these APIs. And our engine is actually independent of the API that you're using. So the engine understands this independent data flow graph that we submit to the cluster when executing a job. And the client creates this graph either out of the dataset API, so the user is programming something in the dataset API in Java or Scala, and then the optimizer is optimizing it and generating this data flow graph. For the stream, we have a graph builder, which is also doing some simple optimizations, and then it's also submitting it to the engine. But the engine actually doesn't know whether it's executing a batch or a streaming job. It's just a different configuration of the engine. So also our batch jobs are executed in a stream fashion. So for example, it might happen that your join is executed as a stream. So one side gets consumed first, and then we stream the big side of your join through the system. So these are the APIs. And as I said already, you can process, or you can do batch use cases on a streaming engine, because we can just have some more assumptions about the data when we know it's a batch use case. Because in batch jobs the data is bounded. We know that the stream ends at some point. And that's why we can do this global window, that's why we can consume the entire stream and then do a grouping or a join on it. So the batch processing is just part of the data stream processing. And as I said, since we have these assumptions about the data, we can do a lot of optimizations. So we have for our operators like join and sort and so on, we have out-of-core support, which means that we can spill to disk if it doesn't fit into memory. We also are able to allocate the elements not on the heap, but we allocate them in byte arrays in a serialized form, and these operators are able to do the computations like joining and sorting on that serialized data. So we don't need to deserialize everything when we compare elements for sorting. We can do the sorting on top of these byte arrays, which is a very compact representation of your data in the JVM, and it makes stuff very robust. The reason why many people, or why Hadoop, or what Hadoop is like mainly doing is they do very robust computation on top of the JVM. And Spark is basically on the opposite side. They are just putting everything onto the heap, and they have to be very careful with the heap, not to run out of the heap space. And Flink is in between these two systems, because we have managed memory. We are very aware of how much memory we are using because we manage memory ourselves. But we have these optimized algorithms also for stuff like joining, which Hadoop doesn't have. And we have the optimizer, which is able to decide on the best execution strategy. So for example, you can execute joins in different ways. So there's, for example, the broadcast join and repartition join. In Hadoop and in Spark, you have to implement this yourself. In Flink, the system automatically picks the best execution strategy for you. So for the stack, we now have added the APIs. The next thing is these specialized abstractions on top. And one of those is Flink ML, the machine learning library. It's currently only for the batch API. So you can mix and match the batch API, the graph API, and the machine learning APIs, because they are all built on the data set abstractions. And you can build nice machine learning pipelines, which is something inspired by scikit-learn, a very popular machine learning library in Python. And we've added a bunch of algorithms that we ship as part of the machine learning library. Another specialized API is Jelly, our graph processing API. I think it's the most popular API on top of the dataset API in Flink. It allows you to represent graphs, so we have specialized data types for representing graphs within Flink. And then you can, so these data types have methods for changing graphs, for getting properties out of the graph. And we've implemented some popular graph processing algorithms like PageRank or connect to components and so on, that you can use to get some first understanding of the graph data that you're having. So let's add them to our stack picture. And the next slide is going to add a lot of more stuff to our graph, to our stack, which is integrations with other systems. So Flink has a very good integration with Hadoop. So we can use all the existing input and output formats of Hadoop. So if you have, I don't know, some fancy in-house file format, you can read that in Flink as well. Flink can run existing mapper and reducer implementations from Hadoop. So you can mix and match your reduce function with a join function or map function of Flink within the dataset API. We also support all the file systems of Hadoop, so you can use NFS or MapR file system, Amazon S3. So they are all supported in Flink because we implement the same interfaces as Hadoop. And we also have support for Hadoop's writable type. So everything in Hadoop that contains user data implements this writable interface, for example, long writable or text or int writable and so on. And Flink's serialization stack has special representation for the writable type of Hadoop. So we can handle these types very efficiently in Flink as well. Then we can execute jobs implemented against Google's Dataflow API. So Dataflow is an API that Google has published, and everything implemented against that API runs on Google's cloud. But you don't need to give money to Google, you can just download Flink and run the stuff on premise. We also recently, so Data Artisans partnered with Concurrent to implement the cascading API. So you can use existing cascading jobs with almost no code change, which means one line. So instead of the MapReduce 2 submitter, you can use the Flink submitter, and then we will just use the same API and everything and submit the job to a Flink cluster instead of MapReduce. And the first performance numbers that we are getting are pretty impressive. So people can use the existing cascading jobs with a much better resource utilization. Apache Zeppelin is a project that allows you to do interactive web-based data exploration. So you can, I don't know, group and sort and join, blah blah blah, and then the result is just visualized as some fancy graphs in your browser. And they have an integration with Flink, so you can submit your analysis to Flink as well. Samoa is a project which has been started by Yahoo. It's a machine learning library on top of data streams, and you can use Flink as a backend for Samoa. And then there is the Storm compatibility layer, and the famous author of the Storm compatibility layer is sitting here, is Matthias, the next speaker. He created a layer that allows you to run existing Storm code within Flink. In two ways. You can either mix and match, so you can use existing storms, bows and boats and mix them with Flink operators, or you use the Flink topology builder, which is a one-line replacement for existing storm jobs. So instead of using the regular topology builder of storm, you can use the Flink topology builder. It has exactly the same API, and then you can submit your storm job to Flink. Matthias also has some thoughts about adding exactly once using Flink's checkpointing mechanism to Storm, which would allow users to benefit from the performance of Flink and also get better processing guarantees while having the same code, which is, I think, pretty exciting. And it's a very easy way of getting started with Flink. Last but not least, we have different ways, different deployment options for Flink. There's the local option, which allows you to start Flink out of your IDE. So you can basically download or just add Flink as a dependency in your Eclipse or Maven project. It will download all the dependencies and just click play, and then it starts the cluster locally. You don't need to download any files or unpack them or anything. This also allows you to do debugging in your IDE, so you can set breakpoints and see how Flink is, what Flink is doing. So it's running exactly the same code as on the cluster. For cluster, we have two main options. One is the bare metal installation. You just put the Flink directory on all the machines, and then you spin up the cluster. Or you deploy Flink on Yarn. In this case, Flink is also taking care of container restarts. So if one machine fails, we will make sure that it allocates a new container. And we also support secured setups. So we support secured Yarn and secured HFS setups. And some external contributors currently adding also support for HBase, so that you can also access secured HBase setups. So we are through. I've completed the stack picture. So you have deployment options, the runtime, the APIs, and then higher level APIs on top of these APIs, which are use case specific or for different systems like cascading. I don't know how much time we have left. I'll make it quick. I saw that the pizza has already arrived. So in Flink Forward, we had a lot of talks from companies which are using Flink in production. One of them is Bouygues Telecom. It's the third largest mobile provider in France. And what they are doing is they want to produce quality of experience indicators. I had to look it up. So instead of quality of service, where you basically analyze machine data, you also want to analyze how is the user experience. And they are using Flink streaming for ingesting data from their mobile equipment into a real-time search index. So when a customer of them calls and asks, hey, why is my phone not working? Then they want to be able to look up within less than 60 seconds, what's the issue? Is it the phone? Is it the network? And so on. And they want to go into further use cases. I think Bouygues is the first production user of Flink streaming. Before they put it in production, they also were doing some experiments, and they used the biggest Kafka topic that they had at hand. It contains 2 billion events, which is 480 gigabytes of compressed data, stored in 10 partitions, and they used only 10 task managers, so only 10 workers of Flink with 1 gigabyte of memory each. So they were using only 10 gigabytes of memory in total. And what they did, they just told Flink, okay, just take this entire topic and read everything. And this topic contains the data of 1 day, and Flink was able to process it in 1 hour. So they have a lot of room to grow for their use case. And also they also looked at the latency, so the end-to-end latency from when the events are produced in the network equipment until it ends up in the index. And the end-to-end latency was less than 200 milliseconds. So they're pretty excited about Flink. Another company which is doing a POC with Flink currently is Capital One, a large bank in the US. And they are replacing a proprietary log analysis software with the open source stack. So they were evaluating whether they can do it cheaper. And they put Kafka and then Flink as the analysis layer, and within Flink they do stuff like real-time alerts, so they want to see whether there are fraudulent devices doing transactions in the bank. Then they do window aggregates where they collect data of certain time frames, and they do simple transformations, because in these indexes, so in this case they were using Elasticsearch, they want to add data before they put it into Elasticsearch so that users can access they have weird IDs for some category, whatever. They have weird IDs, and they use these enrichment or transformation functions for putting the name there. And they put it into Elasticsearch, and then they use Kibana to analyze the data. And as a side product, they are also putting the stream into HFS using Flink's rolling file sync, which is then used by the batch processing layer. Another company is Otto. which is the second largest retailer in the world after Amazon.com. I think a widely unknown fact. It's, I think, because they have so many small websites. And they are using Flink, or they are looking into Flink, for having a unified tracking of all these websites. There were, I think, 2 talks at Flink Forward, and there's a blog post in the Data Artisans blog where they describe what they're doing with Flink. Quickly, to give you a view into what's currently happening in the Flink community. So as I said earlier, we are currently working on the 0.10 release. It will bring master high availability to Flink. So there will be no single point of failure anymore. You can shoot whatever JVM you want, Flink will continue running. We've improved the monitoring API, the monitoring GUI. So it's now a fancy hipster web interface where you can click and see what's going on. We've done a lot in the field of windowing, event time processing and so on. If you survive the pizza, you can learn about it from Matthias. And we made the streaming API stable. So we removed the beta flag and we reworked the API, and it should remain pretty stable for the next release. And the next release is 1.0, which is mainly about API stability, so to guarantee that we are not breaking anything for the upcoming minor releases. If you want to learn more about Flink, check out the resources of Flink Forward. All the slides are online, and we're currently uploading the videos on the YouTube channel. It's a really great way to see what the different companies are doing with Flink, what research groups are doing and so on, performance and so on. Another way of learning more about Flink are the user and dev mailing lists. Also our Twitter account and these 2 blogs. So the Flink blog, which contains technical articles from the committers, and the Data Artisans blog, which also contains articles where we describe what you can do with the system, for example, a hands-on Kafka tutorial. We will soon publish something about Windows. So windowing and event time processing in Flink. If you're, if you have trouble with Maven, you can just join on our Flink IRC channel on Freenode, and we can help you. If you want to get your hands dirty immediately, you can start Flink on Yarn with these 4 commands. So afterwards, you have executed word count with Flink on Yarn. And that's it for my talk. Thank you for your attention.